What do you got?
So, a bullet of mass equals 0.001 kg, embeds itself in a wooden block with a mass of 0.999 kilograms, which then compresses a spring that...
So the K value is 150 newtons per meter. Have you guys talked about K values in springs?
I don't
He mentioned
remember
something
much
about
about it.
springs, but I don't know if he talked about like...
So a K value, and the most common units you'll see is newtons per meter. What that's saying is that if you push on that spring with 150 newtons of force, it'll compress 1 meter.
Okay. So by a distance of 0.051 meters before coming to rest, the coefficient of kinetic friction within the blocking table is...
Oh man, they give me friction.
Yeah.
That's a tricky one. Usually, I've seen this type of question quite a few times, but I don't know that I've ever seen it with friction.
Do we have to actually use friction, or can you solve it without?
Yeah, I think you'll have to use it. So here's our spring, and it's attached, let's make it a little longer, to a block. And we've got a bullet that's traveling with some velocity, and it's going to embed itself into the block. So what kind of collision is that? If it embeds itself and they stick together?
Inelastic.
Inelastic, okay, because there's no bounce. So we're dealing with an inelastic.
It'd be elastic, right?
If it was like bulletproof glass or something, and the bullet hit and then bounced off, that would be elastic. But if it's inelastic, that's when it sticks together and they like kind of become one object.
Gotcha.
With combined mass. Okay, so let's write some of this stuff down. So we know that the spring is going to get compressed some during this collision. We can call that change in x, and it was equal to what?
150 newtons per meters by a distance of 0.051 meters.
0.051 meters. Okay, so that's our change in x. Our K value for our block, let's write that over here, equals 150 newtons per meter. Okay, did it give us the mass of the block?
Yes.
0.999 kilograms.
So we'll write that right here. 0.999 kilograms. I don't know why they don't just call it 1. Oh, is this 0.001?
Yeah.
Bullet?
Yep.
Okay. That makes sense then, because then that way when they combine, it'll become 1 kilogram. So I guess that kind of be nice. 0.001 kilograms. Okay, and then the speed, are you looking for the initial speed?
Initial velocity, yeah.
Okay. So we know this is traveling.
For that distance is... Oh, no, just...
And it's got some v naught value that we want to solve for. Okay, cool. So this requires us to use conservation of momentum. And so that idea is expressed with an equation P initial equals P final. So we'll definitely be using this idea, and we'll also be using the idea of conservation of energy. So energy initial equals energy final. And what are the two types of energy that we are always looking for when we do energy problems?
Kinetic and potential.
Good, kinetic and potential energy. Okay, so let's see where we want to start first. I think that maybe we can do, so momentum initial we know is going to be, since the block is stationary initially, it's going to have momentum of 0 because it's going to be its mass times its velocity, which it's at rest, so it's 0. The bullet's momentum we can't solve for yet because we know its mass, but we don't know its velocity. So let's go ahead and start with looking at the energies, because we can start to get somewhere with energy. The energy that's going to be the easiest to find right off the bat is going to be the, And then another type of potential energy that you guys probably started learning about is potential energy of a spring, as opposed. So before, up until now, we've always just called PE, potential energy, MGY. So that's gravitational potential energy. That's not going to have anything to do with this question because everything's on flat level ground. But we have a new potential energy, which is called spring potential energy. Do you know that equation?
I don't know.
It's 1/2 K change in X squared, which should remind you of the equation for kinetic energy because it follows the same format. Right, we've got a 1/2 and then some variable and then another variable squared in both cases. So they're really similar. So these are the two that we're going to be dealing with in this question. Because like I said, there's not really any potential energy because of gravity. But we do have a spring with a K value that's being compressed some distance. So that's where spring potential energy comes from. Because when we compress a spring, that means we're storing energy in that spring. It's wanting to like recoil and give back that energy. So we can find the potential energy of the spring from this information. We know it's change in X and we know it's K. So we can plug that in here.
Okay.
So potential energy of this spring is 1/2 times 150. And like all energy, that's going to come out to be joules. So I got a pretty small number.
I did 2.195.
Yeah.
This is the right change in X, right?
Yep. 0.00. Just 1 0.
Square that. Yeah, I guess that makes sense. Times 150 by 2. So 0.195.